This is part 5 of the Neurips conversation. I attended Neurips 2023 in New Orleans this year, and I have already discussed a couple of those. This is part 5. Please go back in the series if you're interested in the other ones. Now, this block is, I would call it, theoretical computer science and deep fundamental mathematical statistical concepts that help understand models, whether it's transformers, whether it's generally generative AI. I'm going to discuss 4 papers, and the fifth is actually not from Neurips. It's a PhD thesis that I thought was interesting. Maybe just a little context. I'm reading a lot of PhD theses by people that pop up in the conversation. In this case, it's a person called Yannic here. He's actually a famous YouTuber. You might know him. He does a lot of machine learning stuff. He discusses papers. So I read people's PhD theses, and then sometimes I discuss it because I find it interesting to see where people come from intellectually. In this case, I'm going to discuss just really part of his thesis, not the whole thing. It's about the statistical analysis of generative AI in general and generative adversarial networks. In other words, when the idea is to find statistical let's say footprints of perturbed data that could be either be perturbed on purpose to attack a machine learning algorithm, which was, I think, pretty prevalent sort of in the mid-2010s when Yannic started his PhD. So I'm going to talk about this because it fits into the other 4, which are Neurips papers. It's statistical analysis, it's fundamental thoughts about why do things work, how they work, and what are the things that are vulnerable about it, and what are the things that we can fix about it. So I want to start with tree of thoughts, which is sort of an idea to accelerate transformers. And the idea here is that you decide whatever a thought is, it's a coherent piece of text, and then you have a tree of those. So think of it like a decision tree, but instead of actions, you have thoughts, and they follow certain trees, and then you vote on those trees either through value or voting mechanism, and that way you sort of have a more efficient way to get from a problem set to a solution. The next I'm going to talk about is a paper that asks the question, why do transformers do better when they think step by step, so chain of thought? And they also ask themselves, why do people actually think like that? Why do we, when we want to book a flight to Las Vegas, we think, okay, we have to get to the airport, we have to book the flight, we need to get some lunch, we need to get there on time for the meeting. Why do we do this chain of thought thinking? And the paper studies locality of information, which I think is interesting because the fundamental conclusion of the paper is that when AI systems learn stuff, they put the learned data into some sort of local, think of it really spatially, locally in the network. Certain data is locally adjacent to each other. And then chain of thought works because you can connect those localities with each other. And that's kind of how you make context. How you create context between learned things. So this brings me to the next paper. Why does in-context learning actually work? And some of that paper's analysis is that transformers have the ability to call on algorithms that are useful for particular tasks, and if you give them context, they can do that more efficiently. Then why does chain of thought work? Next paper. The reason chain of thought works better is because parallel complexity of tasks. So there's certain tasks that you just have to do. There's a sequential necessity towards them. And I think one of the most interesting conclusions of this paper is that if you really size up a model to a point where maybe sequentiality can be performed in parallel just by sheer size, then you could get to a sort of a limit where chain of thought and direct inference both work at the same time. But for that, you need scale that's not efficient, so chain of thought is more efficient. Lastly, like I mentioned, statistical analysis of general adversarial networks. This is part of the PhD thesis by Yannic. Here, I would say the biggest takeaway from that, again, it's only the first part, and I'm not going to analyze his PhD. This is not a critique or anything like that. This is just for me to keep my records and also just do my research, and you know, I'm going to explain why I'm doing all this a bit later. But in general, the idea here is, in this particular paper, image classifiers might be biased during training and thus vulnerable to perturbations. But when they learn what the dog is, they don't really understand what the dog is. They learn some low-dimensional, you know, relationships that dogs might have that we humans don't even see. And then when we perturb those low-dimensional, you know, data points, then the model can be completely wrong. This is one of the biggest insights of the paper, and I think it's really, really interesting. And you have to be the way I see, you know, AI in sort of the next year or so is really the focus on data is going to be a lot more prevalent, because clean data, unperturbed data, understanding what is the data that we're feeding those models, those questions will be a lot more interesting and a lot more prevalent and a lot more important to answer. This is not even a podcast. It's December 28, 2023. This is Scream Telco. For the day, the fund is down 4.9%. The market is up 20 basis points. For the year, we are up 123.8%. The market is up 24.7%. We're outperforming by 99.1%. So before I even go there, why am I doing this review of Neurips? What's going on here? The purpose of Orange Capital Partners is to give people a sense for what it feels like to run a hedge fund. We've discussed in several instances, one yesterday actually, how we do this, how we decide what to work on, how we navigate a space. Once we decided to work on a space, all these things have been discussed. In terms of Neurips, it's a conference that sort of encompasses most of the academic work that's been done in the world of neural learning, neural data processing, or machine learning, or AI, if you will. AI is not exactly equivalent to neural data processing, because AI encompasses other things too, but this idea that you can build function approximators through neural nets, feed them data, teach them stuff, and then have them execute some work based on that. This idea has been very, very strong and has had a lot of success in the last 10, 12 years. And that's why neural data processing, machine learning, and AI are currently considered the same thing. I don't think they are the same thing. I think there's a lot more to it than just models and neural nets. In fact, I think the focus on data will become more and more important going forward. I would say 2024, in my opinion, is going to be the year when data will take over. And the reason it will take over is because we're maxing out on transformers in terms of size, at least for now. Of course, we can get more size and more scalability on that front. But I think the biggest insight from Neurips 2023 for me is that the central dogma of machine learning, which is data, model, algorithm, that is reversible. So each part of that can be improved, needs to be worked on, needs to be research done on, and all that stuff. So what this particular topics that I'm going to discuss now entail is, I would say, fundamental statistical analysis of why do models work the way they work? What is the, what are sort of the, what are the mechanisms, the underlying mechanisms? And when you really study these papers, whether it's tree of thought, chain of thought, Yannic's work on generative adversarial networks, locality, whatever you look at, it always comes down to, let's look at the data more precisely, and let's see why it is being, why the training works the way it works. The data that we feed the models determines how these models learn. Of course, the the model and the architecture and the algorithm determines that too, but the data has a lot more importance than we might think. And let's be very, very careful about it. So let's start with tree of thought. So tree of thoughts is a concept that helps alleviate some of the shortfalls of current language models. They particularly fall short in tasks that require exploration, strategic look ahead, or where initial decisions may play a pivotal role, right? And what that means is you want to find a way to plan ahead. You want to find a way maybe to solve some of the problems that researchers have already pointed out are going to be more important in the transformer literature, such as how can we get maybe a bit more inference time, but then longer, more deeper answers. The authors talk about system 1 and system 2, Kahneman's idea system 1, so the reptilian, fast decision making, and system 2, more the planning, the frontal cortex stuff. And tree of thoughts is the idea, which is, think about it this way. You have a problem, which is, write me a poem that encompasses today's political misunderstanding between young and old generations, and do this in a sort of fun hip-hop way, right? This is going to be a little bit more complicated, and system 1, this fast knee-jerk reaction type solution provision that large language models can deliver today, transformers can do that, it's not going to be very good. Now, if we could find a way to develop a longer-term strategic decision-making strategy, we could get better results. And tree of thoughts is, think of it literally like coherent thoughts. In that case, what is a poem? What is a good poem? What is the political, so on and so forth. Like we have coherent pieces of text, which we define as thoughts. And then we have trees. So trees is like a decision tree, but in this case, it's thoughts. And then we vote on which position in the tree to take. We either can do a value-based voting mechanism, we can do a random voting mechanism, or whatever voting mechanism we choose. We can use some ideas of crypto here, proof of stake kind of stuff, proof of work, whatever it is. That's not the point here. And what I find powerful in this paper is the concept of sort of this self-referential decision-making, that transformers have this ability. So because they have a semantic understanding of thoughts and coherent pieces of text, that's due to their autoregressive nature. If you put a couple of words together, they are pretty good at predicting the next word. So they have a good sense for what comes next. And the same way, they might have a good sense for what comes next in the context of thought. So this is the idea of tree of thoughts. And it really solves the problem that I think is, again, is being discussed in the research community more often than not, which is how can we have longer term planning, and tree of thoughts is one possible solution. The next paper asks the question, why do we think step by step? So why do humans think in terms of step by step? And then what can we learn from that as it relates to artificial intelligence? And I think this is really powerful. So what the authors say is our results suggest that chain of thought reasoning is useful, which this is now me, a tangent here. They're questioning, why is chain of thought actually useful? Well, it's because we think step by step. So the question, why is chain of thought useful, is equivalent to why do we think step by step? Now let's get back to the quote. Chain of thought reasoning is useful for language models because, number one, direct prediction is inaccurate for some inference because the relevant variables are rarely seen together in training. And then second, chain of thought reasoning improves estimation by incrementally chaining local statistical dependencies that are observed frequently in training. So this is really the powerful thing, and this is maybe this is why I spoke about when I said I want to sort of combine papers that look deeply into the statistical details of the models and try to understand sort of bottom up what's going on in this particular section. This is this is the reason. This is a good example for what's going on here. So why does chain of thought work? Well, when we train data, often variables are seen together. So you see, you see a football player with a ball, with a helmet, with a score, with fans, with a stadium. Like, these variables are always seen together. So how can you now extrapolate football on a beach, father playing with a son, right? That's not something that the model sees very often. However, the model sees football, again, running, Mahomes throwing. Like, this is going to be very prevalent if you train the model, let's say on YouTube video. You're going to see, very popular YouTube videos with NFL players playing football. Now, how can you chain this to a situation where you're on the beach with your son throwing a ball? How can the model learn that? Well, you can chain it, because what you're going to see on the beach very often is kids playing with fathers and maybe throwing, volleyballs or whatever balls, but maybe not that often footballs, particularly not in Europe. And you could chain that by chain of thought. So let's say, think of football on the beach, like connect that, and then the model will actually be like, bingo, yeah, I've seen that before here, I can apply it there. This is the idea, and I think this really, it just calls this really interesting situation, calls up this situation, or shows the intricacies of the data and the quality of the data, and what it means to actually train a model. Like, the more diversity of data you have. So if I only train my model with NFL videos, it knows a lot about football, but it's not going to be able to connect that with other situations where throwing a football might happen. So if I train my model on a lot of dispersed data where footballs happen in, some people have footballs in the office. That's something that is very unusual if you just train, a data on NFL videos. So again, like, the more diverse your data set is, the less locality you have, the less chain of thought you need. In other words, also, you can have chain of thought making the training more efficient. So you don't need that diverse set of data. You can train locally. You can train a model on what is life like in an office, and you can train a model of what is life like in an NFL game. And you can chain those by saying, well, think of somebody throwing a football on the field, and now think of that, doing that in an office with the constraints in an office, but you can still throw a football. Maybe the boss can throw the football to his employee, and the model could learn that kind of thing. So I think it just puts us in this situation where we start thinking about the data from a perspective, okay, how is it going to affect the statistical landscape, the architecture, the geometry of the weights in the model. The powerful insight here: humans require less learning because they cluster data and connect them with concepts. Locally structured data that then be connected promises to be more efficient for training. What I like about this paper is that they also discuss the structure of training data. This goes back to data comp. Remember, data comp is a relatively small project out of UW, but it really points out the most important thing, which I think artificial intelligence research will have in the next couple of years, which is what data do we use for what model, and how can we iterate around data. The next paper I want to discuss is a paper that answers the question, why does in-context learning work? What is in-context learning? In-context learning is when you give transformers hints, like one-shot learning, for example, is in-context learning. So the transformer is pre-trained in an unsupervised way on lots of knowledge. And like Karpati said in his Stanford lecture, think of a transformer as a compressed representation of the knowledge on the internet. Now, in order to do something with it, there's several paths. One is fine-tuning, but then there's also in-context learning. So you tell the transformer, fromage is cheese in French, and now translate, please, what is house in French, or what does maison mean in English, whichever. And because you gave that one prompt to the model, it will be able to answer that question going forward. In other words, it will be able to translate French just from one shot. When I first read about this a couple of years ago, I was like flabbergasted. I mean, to me, this was science fiction at the point of almost Star Trek, right? But now that I think I understand a little bit better, and this paper really helps me bridge that understanding. So what this paper says is that during training, during pre-training, a transformer learns a set of skills. And what most crucial is the transformer also learns how to apply those skills. So if we prompt, let's say, if we prompt a transformer with a French word, which is kind of prompting almost like a binary type of information. So we tell the transformer, listen, you're going to have to now do a transformation from French to English. The transformer will then be able to choose the right model, whether it's a logit regression, whether it's some sort of least square, whether it's a recurrent neural net, or something along those lines that the transformer can use to actually do that task. So to take English words and then find the most likely representation in French. So the transformer is able to choose amongst available models, algorithms, the one that's most appropriate for the task. What I think maybe another illustrative example is if I prompt some sort of data which is binary. So let's say I would say, this is a dog and this is not a dog. So, a picture of a dog, this is a dog, and then a picture of a cat, this is not a dog. And now show me all the dogs in the next following 50 pictures. The transformer will use some sort of logic regression to do that particular task. Versus if I feed a continuous data, so stock tickers, for example, and then ask predict the next stock tick, it will use more of a least square type, time series analysis. So this is the gist of this paper. It has this ability to, why does in-context learning work? Again, in-context learning is something like one-shot learning or few-shot learning. So the model learns without, this is the key, it's not changing its weight matrix when you do one-shot learning. One-shot learning or few-shot learning is calling on the model's abilities, injecting or nudging the model towards choosing a certain trajectory, a certain algorithm to solve a problem. So this is, you can see the nature here of something like prompt reader, which I discussed in the previous episode about Neurips, self-referential, self-improvement type. You can see the nature of the operating system that transformers are morphing into according to Karpathy, which I think is true, because this condensed knowledge that is represented in the weight matrix of a transformer allows the transformer to semantic planning, whether this is robots planning how to pick up an egg, or whether this is how to choose the appropriate algorithm to solve a problem. In the end, from a transformer perspective, it's the same thing. So again, this is a beautiful example of a paper that digs deep, tries to understand from a fundamental first principle approach, what is going on here under the hood? And why are we successful with certain approaches towards problem solving? Now, the next paper is similar in nature, but fundamentally very different. Why does chain of thought work? Okay, let's be careful here. We asked, why does in-context learning work? Now this is, why does chain of thought work? Chain of thought is a different concept. Chain of thought is a sequential solution to a problem. And the fundamental reason why chain of thought works is because of the parallel complexity of tasks. Now, what is parallel complexity? Parallel complexity refers to the study of how efficiently a computational problem can be solved using parallel computation. So, unfortunately, these papers, like every other scientific endeavor, they have to elevate themselves to the language and culture of scientific people, and therefore it often sounds a little bit more complicated than it should. What they're saying is, look, a lot of tasks can be solved in a sequential way. That's why chain of thought works really well. And again, transformers, because they have condensed knowledge of the internet, there is a tree that a path, a sort of a tree. This goes back to also chain of thoughts, of course, but tree of thought, excuse me. But let's stay with chain of thought here. Why does it work? It's because of sequential decision making. And actually, the authors use dynamic programming as an example to show how dynamic programming can be approximated with transformers. They're really good at that. And this is really a very, very important door that's opening up. And this goes back again to the self-debugger. This goes to the prompt reader and all the other endeavors that, in my opinion, DeepMind is trying to apply. That they did that in the first big paper that brought them that brought them on the map, which was their sort of Q-learning paper when they did the Atari. When they solved the Atari problem. This is probably what OpenAI is talking about when they talk about Q-star. It's fine. Look, I'm not going to get into that conversation, but the point is the following. Look, you can use these transformers for a lot of things, but if you can find a way to have the transformers through self-referential self-improvement improve themselves and improve the way they improve themselves to solve certain problems, and using chain of thought as a fundamental principle for this, which is simply, again, it's a sequential approach towards problem solving. You can solve a lot of problems. Now, what this paper is also saying, which is really, really important, is there's probably some sort of mathematical proof that you can at least try to approach, where you can say, if we have a big enough model that is deep enough and wide enough, so enough layers and enough size per layer in terms of parameters or neurons, and then parameters attached to those neurons, then maybe we can parallelize sequential problems. In other words, we could have a gigantic model with trillions and trillions of parameters that has the ability to actually, in one shot, directly infer a solution that might require chain of thought or parallel programming or something like that. It is possible in principle. It might not be efficient though, because you have this gigantic model that needs to store all the knowledge, not just of the internet, but also of the sequential processes that are necessary to solve a problem, when maybe we could do that much, much more efficiently if we did it through chain of thought. The way I kind of conceptualize this is the following. Let's imagine you're standing in the Swiss Alps or in Queenstown, New Zealand. Who's ever been there knows what I'm talking about. You're at a road and there is a bunch of massive mountain chains in front of you. And your task is to figure out, in one of those, your wife's car just broke down and you have to go get her. Now, you can solve this problem in sort of a chain of thought way, which is, I'm going to go, there's, let's say, 5 roads I can take. Each one is very windy, and I can maybe have a certain algorithm where I go down this first road, I go a certain way. If I don't find her, I go back, because I figured, look, if she got this far, she might, be already, I would have found her because the car only has this much gasoline, whatever. I have a certain algorithm where I try to dynamically solve the problem. Or I can just brute force, go through each valley from beginning to end and figure it out. If I have enough computational power and I can do this fast enough, I can do this brute force. I don't need to do this sequential problem solving. Now in real life, of course, we don't have that. We have to do sequential. You have to go left first and then right and then to the middle and stuff. But in principle, a computer could do all of them in one. Now, this is sort of what quantum computing is trying to do with inference and the entanglement stuff. You could, in principle, solve sequential problems in parallel. This is the power of quantum computing. This is the power of large transformers. And this sort of weighing between sequential and parallel, I think is going to be a big deal going forward when it comes to ComSci and traditional classical ComSci and AI, and of course quantum computing. This realm is not finished. We're not done with that. There's a lot more to explore here, and I think chain of thought is one of those avenues. That's why this particular presentation was full of people, and really you could sense the energy in the room. There's something to this which is a lot more than just, oh well, yeah, we can solve this sequentially, right? This is fundamental. Authors conclude the paper with some interesting foresight. Firstly, they say, while this paper investigates why chain of thought enhances the expressivity of large language models, we do not yet answer how the chain of thought generation process is triggered by specific prompts. Revealing the relation between prompts and outputs is valuable for better harnessing of large language models. Secondly, it has been empirically observed that scaling the model size significantly improves the chain of thought ability. Theoretically, understanding how model size plays a role in chain of thought would be an interesting research problem. I think this, to me, is the absolute holy grail of theoretical computer science, of, you want to write papers in terms of what size means to the parallel complexity of computation and how you can solve that, and then maybe throw in there some quantum computing concepts. I think you're onto a Turing Award type paper in that context. Lastly, I want to talk about a paper that this is Yannic's PhD thesis, written actually 2 years ago, or published 2 years ago. So this is not a Neurips paper, but the reason I put this paper in, because it is also a statistical analysis. It is, I would say, one of those deep first principle sort of looking into the guts of a model type papers. That's why I included it here. Sorry, Yannic, if you listen, I'm probably going to butcher it, but I'm only going to talk about one section of it, which is the section where he talks about the statistical properties of adversarial attacks to let's say, image classifiers, which is like, think about it like you can perturb images a little bit and then have the classifier completely go havoc, not recognize dogs, and call women monsters and men are tanks and whatever, like completely off. Like you can totally disturb a classifier. Imagine, of course, let's say in the self-driving car space, really dangerous. The Chinese, I'm sure, have their problems in their surveillance state with that. Like image classification, image recognition is a really important task already, super important for many robotic solutions, and some good, some bad, but whatever. Now, what adversarial attacks can do is, with very low-level perturbation. So let's say you have X, Y, Z axis of a picture, right? You can just perturb the X a little bit, something that a human eye wouldn't even see, like let's say a dog or a cat or whatever, and then the classifier would not be able to classify this picture anymore as a dog. Now, what Yannic is doing in this first part is looking at statistical sort of foot marks or fingerprints of adversarial perturbations, right? So he's trying to answer the question, if we look at, in this case, the last layer before the activation layer of a network, if you look at the neurons and we statistically analyze them, so let's say a perturbed versus a non-perturbed model, do we find, is there stuff we can detect where we can deterministically then later on detect that, hey, this model was perturbed, be careful, versus this model wasn't, and even maybe better, when it's perturbed, we can actually fix it. because if we know what the reason is for the adversarial sort of damage, we can maybe undo it. And I think this is interesting in many ways. I think it shows what people are working on. The reason I read these PhDs is really, PhD thesis is to understand where people come from intellectually, to understand a little bit what certain also academic institutions are doing, in this case the Polytech in Zurich, and also, of course, to understand what is the research that people are investing a lot of time and effort in, that, you know, hopefully will be fruitful in the future, maybe not, but it's interesting to know what academia is doing. There's a quote from this a paper that I want to read, which I think encompasses really the importance of the paper. Instead of viewing robustness and adversarial examples as a binary phenomenon, robust or not robust, the authors, in this case Elias et al., proposed that robustness lies on a continuum. There are degrees of robustness, and adversarial examples exist as a natural consequence of the model's capacity to generalize. Machine learning models tend to learn low-dimensional features that are not really part of the image and can be perturbed easily. This is key to designing better models. Data collection, annotation, and iteration around data in training is key, in my opinion. This is now me adding to it. I don't know how much there is quoting, how much is me, doesn't matter, but think about it this way. When we classify a dog as a dog, the model doesn't really know what a dog is, or at least doesn't see it the way we see it. It might actually learn some very low-dimensional data patterns that we don't even know, and when we perturb those low-dimensional data patterns, that's why it fails. I think it's almost clear that that's what's happening, because we know that very low-dimensional perturbations can destroy the ability of a classifier to work. We might know exactly what it is, but we know roughly where to look, and that's part of Yannic's paper. And therefore, it's interesting to dig deeper into the statistical analysis, understand what are those low-dimensional patterns that are actually leading a model to classify a dog as a dog. This goes back to a presentation way back that I attended at Stanford, where I looked at a paper presented by a Korean lady, I forgot her name, and she spoke about the geometry of data. And she spoke about how you can sort of think of image classification as any kind of object, a dog, a car, a house, has there's the Hilbert space of possible vectors that any object can have, and then an object is defined as its own little subspace within that Hilbert space of vectors that define that object. And image classification is trying to find that subspace of vectors that define a cat versus a dog, etc. And what Yannic in his paper is saying is that that vector space is much bigger than we humans actually perceive. He calls it low dimensional. I mean, it's not just him, that's what the literature calls it. And that low dimensional vector space can be perturbed, and therefore the classifier can be damaged. So if we understand that perturbation, we can learn a lot about classification and machine learning. This is the fundamental idea of this paper. And I think this leads me to the conclusion that we need to pay a lot more attention to the type of data that we feed the models. We need to understand the data, or if you want to use that vector space notation, we need to understand what is the subspace of Hilbert space that defines a dog? What is the subspace of Hilbert space that defines a chair? If we look at it more generally like that, I think we can find better ways to classify images. We can find better ways to protect ourselves against adversarial attacks, and we can, in general, better understand models. So to summarize, this part 5 of Neurips is a conversation about models that, in my opinion, have one thing in common, which is they dig very deep into the statistical geometry of models. They look at why certain things work, such as tree of thought, chain of thought, and so on and so forth. They try to understand why, let's say, generative adversarial networks can be attacked by adversarial perturbations. Why does that even work? They have some quantifiable paths towards either improving the models, protecting the models, and they really give us some fundamental, deep understanding of what is it we're actually doing here. And I think chain of thought was the biggest one for me, because it really opens, to me personally, it opens up this big door of, okay, what is parallel complexity of a problem, and can we parallelize parallel complexity? Sorry for that, but what that means is certain tasks are better if we do them in a sequential way. Certain tasks can be done in parallel by definition. Now, can we, through model size or computational techniques, such as, let's say, quantum computation, approach parallel complexity in a sequential way? And therefore maybe have model size or computational approaches solve some of the parallel complexity problems, and therefore have more efficient models or more efficient training. So I discussed 5 papers here, 3 of thoughts. Why do we think step by step? Why does in-context learning work? Why does chain of thought work? And finally, a statistical analysis of generative adversarial networks and why they work. Thank you.